For our next problem, let's try to involve something about your chemistry. So I would want to explain something about this reaction. We know that knowing that this is the value of our constant and the unit is liter per mole second, we know that this is a second order equation. And the fact that this is a second order equation, we are given by the general formula. So instead of illustrating this, since it is quite impossible for us to illustrate this expression, then we'll be using 1 over A is equal to 1 over AO, the general equation, to be able to determine the necessary unknown in this case. And in this problem, we're asked to find the change in the concentration of a reaction obeying this expression. We know for a fact that the initial concentration is 2.5 molars or moles per liter. Now, for every reaction, there should be always an initial reaction, and an initial reaction would give us an idea that it is always constant. Imagine if you have, let's say, 2.5 grams of a certain compound, and then it reacts with another compound. You know very well that the initial amount would always be a constant because it doesn't change. The initial concentration doesn't change with respect to time, but the final concentration does. So we know that A is changing, and we know in this case that if A is 3/4 of A sub O, then A at this case is 3/4 of 2.5 m, and that is actually equal to 1.875 moles per liter. But this doesn't mean that A is a constant. This means that this is only the value of A at a certain condition. So now if we plug in these values with our general expression, we know that 1 divided by 1.875 plus 1 over 2.5 plus K, which is 0.35, and then T, we can obtain the value of the time that we're looking for, wherein this time would give us the final concentration, that is 1.875. So this will give us 8 over 21 second. We could just say that at 8 over 21 second, the final concentration of these 2.5 molars is just 1.875 molars. But the question is, what is the change in concentration? So the question is dA over dt. That is what is asked in this problem. Knowing that this expression is asking for such change, we should be using the general equation again to implicitly differentiate it. Okay, so if we have 1 over A, so we will implicitly differentiate this with respect to time. So this is the second portion of that equation. So we have 1 over A sub O plus KT. So basically, what I'll be doing to the general equation is that I will implicitly differentiate it. We know that this can be rewritten as A to the negative 1. So basically, if you would be differentiating that, the derivative for this is A negative A raised to negative 2, and then that's dA over dt. And then this is equal to, this one is a constant, so you know very well that if you would differentiate this 1 over A sub O, you'll just get an answer that is a constant. So that would be 0, that's 0, and then plus. Now KT can be differentiated in a way that K is a constant, so you'll be left out with K, and then we multiply this with dt over dt, which in turn becomes 1 because dt over dt is simply equal to 1. So in this way, we're left out with dA over dt being equal to K, and then we multiplied with A squared, and that's the negative of dA over dt. So dA over dt, following this equation, we know that A squared is 1.875, so we have the negative, then square, and then K is 0.35. So if you have M unit here, and then you have liters per mole second unit here, we know that that would cancel 1 M, so we're left out with M per second. So dA over dt is simply equal to negative 1.2305 moles per, or molar per second. So this is our answer for this problem. So I hope you've understood what happened here. It's just we already have the general equation, and you just have to implicitly differentiate that to get dA over dt, which is the concentration at any time t, or the change in the concentration at any time t. But to do that, we need to find the values of our a and t. Actually, we don't have to find the value of t based on this expression. I just actually solve for it, but based on this, you don't have to like find this, but there are ways that we can use this t. For example, if I didn't use differentiation in this way, if for example I tried to multiply both sides by a, you will be left out with a kt, wherein you need to implicitly differentiate that, and you'll be having something like kt dA over dt, which will leave you something like a need for the value of t. But in this case, the solution doesn't need it, um, so that's it. We don't have to like find this one. And to explain something about this negative side, that only means that our concentration is changing and it's decreasing with respect to time. And you can also actually notice that in the problem itself, when the concentration is 3/4 of the original, that only means that as the time progresses, the concentration is decreasing. That's why you have to expect that the change is negative. Now for this problem, let's have a review of your ideal gases. I have the problem here, and the one in your module is actually incomplete, so I just have to emphasize it, and I just wanted to make you understand that there should be another finishing condition that states that consider that the temperature becomes 260 Kelvin and changes at a rate of 1.75 Kelvin per minute. So I want you to read the problem first and go back here after you've understood it. Okay. So this problem is, if you would visualize this, we have something like a container. In this case, it's a chamber, and then that's a messy one. Let's have a good drawing. So you have a container. Let's make it cylindrical na lang, no? And then the condition on the initial is that it is at STP. So we know that if it's STP, we know that the temperature is 273.15 Kelvin initially, and then the pressure is at 1 atmosphere. And then of course the volume is dependent on the number of moles. Okay, so in this case, also in the given, it is stated that on a final condition wherein some of the amount of this helium gas escaped from the chamber, because for example it was initially closed and then it was opened, so basically may maglalabas dyan na helium gas. So at the final condition, the pressure becomes 0.7 atmosphere, and then the temperature becomes 260 Kelvin, and then we know that the change in the pressure is per minute, and then for the temperature, that is also decreasing because initially we had 273, so we have negative 1.75 Kelvin per minute. Now the question is, what could be the rate of the gas at the escaping of the gas, so that's in mole per minute. So we're typically asked for dN over dt in this case, so we need to find dN over dt. That is the rate of change at which the number of moles is actually changing. So to do that, we already know one equation for such ideal gas behavior, and we know that that's just this PV equals nRT. So we know that PV is equal to nRT, and in this case the volume is fixed. So how do we find this volume? So the initial volume will just remain. So if we have V here, that just will be equal to the V at the final. So to do that, we know that we need to take the number of moles first, because if we're able to find the number of moles, then we can now determine the value of the volume. So N is simply the number of mass divided by the molecular weight of that material, and we have 40 grams of helium. So in this case, if it's helium, we know that for every 1 gram of, for every 1 mole of helium, we have 4 grams of that. So this is equal to 10 moles. So basically, we have 10 moles of initial gas on the inside. And then The volume for that would simply be 22.414 liters because it's in 8 STP times 10. So basically, we have 224.14 liters of volume. And that's the same thing here. At the final, we still have that kind of volume. So we go back with this PV is equal to nRT, and then we try to implicitly differentiate all of this expression in terms of time so that we can obtain the general expression that we'll be using. So we have P times dV over dt, and then plus V times dP over dt. So I'll be differentiating all of the variables muna, disregarding this R. So I'll factor out R kasi siya ay constant, and then we multiply this with N times T, which is a product. So we have N times dt over dt, and then plus the temperature, and then dN over dt. Okay, so this is the general expression of the implicit differentiation of the ideal gas law. And now we cancel this expression because we don't have any change in the volume. So we're left out with VdP. So we have VdP is equal to R times N times dt over dt plus the temperature times dN over dt. And we actually need to find this dN over dt. Now, we can already plug in all the values. We know that the volume is the same. So we have here V. And then dP over dt is this negative 0.05. R is the universal gas law constant. So we'll be using the units that would fit in this. And then N. So we need to determine N at the final phase of this equation or given. And then we also need to find the temperature at this point. But it's already given pala here. That's 260. So we just need to find the value of N. So going back with that, before we use this expression, we need to find N at the final condition. So PV is equal to nRT would still be applicable, but we know that it's no longer at STP because the temperature and the pressure has already been changed. So, but still the volume would remain as it is. So we have the pressure that's 0.7 atm, and then we have the volume, which is 224.14, that is in liter, and then we have the number of moles, and then multiplied with the universal gas law constant, and then the temperature in Kelvin, so that's 260. So we're left out now with the value of N, and that is equal to 7.3538 moles. So this 7.3538 moles is the number of moles that is inside this chamber. Now, if you would be doing something like 10 minus 7.3538, then that's what already escaped from this chamber that decreased the pressure and the temperature. So, by the way, we already obtained this N. So now we've got no problem with this expression. Now we can obtain the value of dN over dt from this expression. So the volume is 224.14 because it's constant. It stays all the same until the end. So that's liter. And then dP over dt is negative 0.05 atm per minute. And then this is equal to R. So R is 0.08206 atmosphere, and then liter per mole Kelvin. And then we multiply it with N. So N is the one that we obtained right here. So that's 7.3538 moles. And then times the change in temperature. So we have negative 1.75 Kelvin. So we have negative 1.75 Kelvin per minute. And then we add the temperature final. So that's 260 Kelvin. And then we have dN over dt. So this is the one that we need right here. Okay, so solving for this, we get dN over dt is equal to, so we have negative 0.4758 moles per minute. Okay, so this is our final answer. So in this case, we could just give a conclusion that as the time progresses, for every minute, the number of moles changes by by negative 0.4758. So that means that it decreases as the time passes by. So this is the answer for this problem, and you won't be able to answer your module because it actually lacks some given right there. But if you do, then you'll just end up with dn over dt would be equal to 0. So if you'll just be solving without this final statement. I think I forgot to write that before. Okay, so that's all for this problem. I hope you've understood some concepts right here, but just to give you a quick recap, there always be some kind of concepts that we need to apply in solving for related rates and optimization. The one that we did here is knowing all about gases and STP. In this problem, we try to go back with the relationship of reaction kinetics with chemical engineering and calculus, and how it is used in solving for the rate of change in the concentration. In this way, we applied the idea of expansion of gases. So, and then in this problem, we have this some kind of flow rate based on the conical arrangement. And lastly, we have this kind of figure that is not common in geometry, because that's actually a spherical segment and not the hemisphere. So I hope that this related rates example of giving you some clarification on what to expect in the exam. Okay, so I'll be giving out some practice sets that you might want to do so that you will be able to understand how these processes work and how we could apply all of these in terms of for higher engineering and higher chemistry subjects. Okay, that's it for our related rates. I hope that you understood how this problem worked, and it is actually one of the toughest topics that you will encounter in diff cal. So kung gets nyo na siya, the other topics would be a lot easier. But I hope that you will not forget these topics, because I know for sure that you will come back to these discussions in order to understand again the differential equations and your unit operations on how we actually solve for the maximum or the minimum value of certain topics. And of course, those values that need to be determined using the idea of the critical points that we use to do in extreme value of functions. So with that, I hope that you would study a lot, and at the end of the day, we're still coping up, even if it's still this pandemic has really taken a toll of us. But even though it's really quite a long time that we're having a pandemic, we don't actually get used to it. So don't stress yourself too much. Just do your best as always. And if you really have questions and clarifications, I'm very easy to reach out as a person. So you can always ask me about these topics. And then if you're finding it difficult to submit the requirements because of the current situation, then very open to listen to your problem if you want to. So with that, I hope that you study well and take a good care of yourself. Okay, so stay safe, future engineers.